I was speaking to my new old girlfriend, and she asked me, "How are you?" She asked me, "How you are?" So I said, "No." She wants to know. No, she wants to know if we're making any progress. She's she's tracking the progress that I'm making. She wants to know. Yeah, I mean, I told her about it, so she, because I told her that we're writing a paper together. Wait, are you Alemano? Elmano? Oh,
Elmano.
no, there's somebody
Mm.
else. Let me give you the link. 1 second. We're being asked what is the topic, so let's bring up the topic too. Let me give you the link. Wait, let me put the link in the chat, and let me put the link in the side chat. So it ends with a SU.
Okay.
Okay, so what is the topic, hermano? We're going to review a video by, let's look at the history. Dialect, yeah. Let me see if I can find it. Oh, let me let you in. I guess you love dialect. Let me find the video from dialect.
Yeah, it was up there. I've already
Oh,
seen
you
it.
saw it?
Yes, it's up there. Up, up. There it is.
This one?
Yes.
Okay. I mean, they sound like what I sounded like in the beginning, the first week of my research. I was suspecting that Einstein. I
Uh,
mean,
no, they sound a bit like they sound like they're nitpicking, but what they're actually saying is important.
it's
This one.
yeah, but I think they're off. Let's listen to them.
It's muted.
Yeah,
Principia
let me
Mathematica
start over.
in an obscure passage tucked away in the scholium of his famous work Principia
I don't know what a scholium is. And I listened to them. I listened to what Newton said. I didn't understand what he was saying.
Okay, I'll
Mathematica
explain.
You should not need to reference Principia if you feel there's something wrong with Einstein.
Yeah, but it's
Isaac
okay to do it.
Okay.
Newton left an ominous and cryptic warning to his readers.
Well, if it's cryptic, then we don't really know what he said, what he
No,
meant.
we know what he says. Let's get
Okay.
to it.
Relative quantities are
Let's see. Wherefore, relative. What was he talking about before? And being carried together with their heavens, partake to their motions, and as part of
Doesn't sound relevant.
revolving whole endeavor to recede from the axis of their motion. Wherefore, relative quantities are not the quantities themselves, where
Whose
names
names they
whose
bear?
names they bear. Let's listen.
not the quantities themselves whose names they bear, but sensible measures of them.
Yes.
Okay, that makes
So
sense.
this is exactly what I was. I mean, this is obviously one of my realizations was that we're not measuring. That there is no such thing as time. There's only a clock. We don't know what time is. All we know is what a clock is.
No, but this is important because of for example, length contraction.
No,
Like
no,
it's
no, no. But
basically no,
no,
but
no,
it's relevant for that because it's
no, no.
basically saying that that the measured length is not the actual length of the
That's
object.
fine. That's fine. But even before you get to contraction, just length and just time. There's no such thing as length. There is a meter stick. There's only the way you measure. The fact that you think that you measure length, that's very nice. but but you don't measure length. It's just a measurement. You could say that it's correlated to that abstract notion called length, but you don't know. All you know is what you do. All you can report is what you've done. You conducted an experiment. Tell me about the experiment. Well, I built a clock and I measured 1 or 10 ticks on the clock that I built. Here is how I built the clock. Here is my report. And the same thing for the length. I created a meter stick. How did I create a meter stick? And here is how I used it, and this is the result that I got. That's all that you can report.
Okay, that's basically the point of Newton, really. It's
Yes,
not making further
definitely,
suggestions.
definitely. But this, I don't think this is what
But
there.
is no, but this is still important for this
Yes, but it's
because
not. This is
like
not.
is but in relation to relativity and what relativists
No,
claim,
no. This has nothing to do with
relativists no, it has
nothing.
to be, no. I mean, it starts by mentioning relative quantities, so it has to be
No,
relative.
it's nothing to do with
No,
relativity.
but that's his point. You
No,
have to try to understand what the
no.
point that Newton is trying to make is.
No, 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 no. This has to do with the very. It's deeper than that. This is about the essence of knowledge. This is about epistemology. We
Yes,
don't.
it's about that.
So it's much deeper than relativity. Remember, there's no relativity. Relativity is just wave mechanics. That we
Yes,
know.
the problem is relativity. They affirm that there is length contraction,
But we. But
which
even
is under what Newton is telling you. Yes,
no,
it's definitely a problem.
Newton didn't. No, look, Newton didn't have any notion of time dilation or of length contraction. This would
No,
never.
but he had some notions of that because there were already relativists during his time. Uh,
But
like
we know.
one of
But
his
we.
opposers was a relativist, like his bigger opposer, Mach. You've heard of him for sure.
Yeah,
As a
I think he was.
relativist, is trying to tell is talking about relativists for sure. Yeah.
No, no, no. He's. Look, there's no. I
No,
am.
he's talking. What he's talking about is applicable to more stuff. Is deeper, but is definitely talking at relativists.
No, no. This is much. Look, I am a relativity denier, right? I don't believe in relativity. It's just wave mechanics. There's no theory of relativity. There's just wave mechanics. So you don't have to convince me. So you cannot use relativity when you talk to me. Newton could not have known about
I'm just describing his claims. I'm not saying anything
no, no,
against
no.
him.
Newton could not have believed in relativity because he was not an idiot. You're not
Okay.
going to convince me that he was an idiot. So Planck and Einstein, I don't know what I don't know what they believed in, but this is not science. This is not. Newton was a believed in a mechanical universe, and Einstein and Planck stopped believing in a mechanical universe. That was their mistake, and that's fine. People make mistakes. I don't think it was intentional. I don't think
No, it
Einstein.
probably wasn't intentional.
What?
It probably wasn't intentional. Like
Yeah, of
very
course.
unlikely to
No, of
be
course it was.
intentional.
Of
There are
course
some
it.
people who say it was, but no.
No, 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 no. That doesn't make any sense. No, Einstein spent the rest of
Yeah,
his life at home, secluded, trying to fit together GR with quantum mechanics and stuff. So, yeah,
yeah.
look, no, Einstein was a pure scientist. So, whatever mistake he made, if I believe it's a mistake, if I believe he's wrong, then I have to assume that. I mean, I don't have to assume, but it's clear to me that he did his best. His
Yeah.
best. He gave us his best. Well, for some of the stuff that he gave us is pretty awesome.
And to be honest, he was already leaning the other side with general relativity. Like he has
Yes.
absolute space and time
Yes.
in
Yes.
general
Anyway,
relativity.
my point is that this paragraph from Newton is obviously this is
I mean,
much
it
deeper.
is he is thinking about relativists. Like he is thinking
No.
about them. He
No.
starts the paragraph with that.
No, no, this has nothing to do with that.
I mean, he starts the
Newton,
paragraph with that. Come on.
no, Newton was not. Look, the only reason Einstein started believing in relativity is because he believed that Michelson and Morley got a null result.
No, 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 no. I think Einstein was always like a fan of Mach's ideas. I think
Who?
he was already
Marx?
Mach, not Marx.
Oh,
Although he was
Mach.
kind of a socialist as well, Einstein. But
Mach. Yeah, I don't
Mach,
know. I don't know enough about Mach,
Mach
but
was basically like the first big
no, I
relativist,
look. I
and he was
think
a critic of Newton.
okay. Look, I think that Michelson and Morley's failed experiment threw everyone off. This was just too much. It was too
Yeah,
much.
they just couldn't explain
Yeah,
the whole
it was
thing.
too
So then they
much.
settled for Einstein because the theory of Einstein is not like he excluded. Because we've already read his paper. In his paper, he says something like, therefore we no longer need to consider the any media. He never said it didn't exist. He said we don't with this theory we don't have to consider the media, which
Let me
kind of
just
proves the
copy.
paradox. But
Let me just copy. Let me just copy paste.
okay, why their
The
comments?
the
On that?
name. No, that we're responding to this video.
Oh, okay.
Responding to.
You can. I think you can set it up as a video response. No,
No, I don't think YouTube has this any longer. They canceled this
really?
option. I think so.
Why people were
Uh,
harassing people with that? Something.
I don't know. Responding to 1 second. I'm not even in full view. Okay. Anyway, who is El Mano? Who is
I
this
have no
guy?
idea. Oh man, no. I don't know. You worried that he knows you?
No, I'm not worried that he knows me. He's writing. No, no, no. Oh, no, no, no. He's just. He's writing. The comments that he's writing are illegal. Like he's trying to get me banned from YouTube.
Oh, now I
So
see.
let me suspend him.
Yeah, just ban him.
Let me see. So channel activity, go to channel pin, put user in timeout. 24 hours.
Nice.
Okay.
Okay. No, now he's got one person watching. It's me.
Anyway, so look, this is very deep. This is deeper than relativity. This is about epistemology. This is the very foundation of science. What is like what what is the definition? It's about it's it's about the notion of a definition. When you define something, a quantity, it's about that you're never defining a quantity. All you're defining is the measurement of the quantity. All you can define is how you're measuring something. You cannot talk about the thing itself. Let's keep listening.
And by the names time, space, place, and motion, they're sensible.
The first thing he mentions is time. So time I keep hearing these videos from all these,
Yeah, but he's mentioning it as a measure, so it's okay.
no, but there's all these videos from all these physicists, and they say we don't know what time is. What is time? Time keeps eluding us.
We should
Yeah,
probably read
because
Newton, like the
yeah,
father
it's
of physics.
no, but
They
the
don't
answer
like that.
no, but the answer is we don't know anything. All we can know is what we define in terms of how we
Time
measure
is a
things.
measure. Time is a measure that we make. So just like
Everything everything is
Yeah.
a measure. Everything you want to talk, everything you want to talk about, everything you want to discuss, all you can discuss is the process of measuring. You can never discuss the thing itself.
measures are to be understood, and the expression will be unusual if the measured quantities themselves are meant. Those violate the accuracy of language who interpret
Exactly. This has to do with
Yeah,
language.
it has to do with
This is epistemology.
yes, it's philosophy basically. It's being
Yeah. No,
it's just trying to be as logical as possible.
but the foundation of science is philosophy,
Yeah,
obviously.
these
and
words for the measured quantities. Nor do those less defile the purity of mathematical and philosophical truths, who confound real quantities with their relations and sensible measures.
yeah, it's perfect.
Hmm.
This strange and dire paragraph appears to be cautioning its reader against making some dangerous philosophical misstep, some type of erroneous conflation in reasoning. But of what sort exactly?
But this has nothing to do with Einstein's mistake in the theory of relativity. Nothing to do with.
It does. It does. Like all relativists make this mistake.
I don't think so. The
Yeah,
mistake,
they
they don't
call
make. No, no, no.
when
There's
you
no.
do something like linked contraction and so on, like, and you start.
No,
But I mean,
no,
it depends on how you do it because you
no.
could like just say apparent linked contraction, which would be fine.
Wait,
But
I cannot hear you. What?
you can say apparent linked contraction, which is fine.
No,
But
no, 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 no,
you
no,
should
no.
never say that the quantity is the thing you measure, and that's the problem of relativity.
No, that's. I disagree. No, no,
If
no.
you just say,
No, 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 no. Relativity makes correct predictions. Relativity is
yeah,
right in
so
the predictions it makes. The problem with the theory of relativity is that it assumes a constant speed of light. But a constant speed of light, you don't have to assume it if you just assume the ether. So the theory of relativity really just assumes the ether, but claims that it does not. There is no ether. So that's the only problem with relativity. That really, it's proof. Ultimately, the theory of relativity is the ultimate proof, as if we needed more proof that there is ether. But for
yeah,
some reason, Einstein said we no longer need the ether. But the entire paper proves ether. It screams ether. The constant speed of light is ether. That comes out of the assumption of ether. So, but Einstein had to deal with the null result from Michelson and Morley. So he said, I don't know. And then he came up with this mumbo jumbo in which he basically said there is ether and there is not. That's the problem with the theory of relativity. That it's a mess. It proves ether and claims there is no ether. So my
yeah. It
position is
requires. It's like the only physical explanation possible for the theory of relativity is ether.
correct,
Yeah,
but
that's
the paper
basically.
itself, right? But the paper itself says that there is no ether.
No, the
So
paper says that we don't need ether to explain it. But yeah, if you put everything on the abstract, you don't.
exactly,
Yeah, so
exactly.
that's what you.
If you abandon logic, if you say okay, we're
Abandon reality.
abandoning.
Really, it's even worse.
Exactly, exactly. If you say we're abandoning logic, we're abandoning reality, then yes, you can say that let's assume ether and also there is no ether. 1 plus 1 equals 2, but also 1 plus 1 is not 2. Yeah, it's okay. We don't have to be logical. That's the problem with Einstein's relativity.
It turns out understanding the nature of Newton's warning here is no inconsequential task, because some 200 years after he issued it, a 26-year-old graduate of the Polytechnic Institute in Zurich, and the only individual in his class to not receive an assist.
Okay, that's
Okay,
totally ad hoc.
yeah, that's a low blow. They shouldn't do that.
Yeah, That's complete ad
Well, and
hominem.
it's completely irrelevant. It actually
Yeah,
shows how completely irrelevant it is.
yeah, yeah,
That he
yeah,
was the most successful of them all.
yeah.
distant ship position upon graduation would precisely fail to heed this warning, and subsequently plunge the philosophy of modern physics into total freefall. 120 years later, it will be us who
No, it was the Michelson-Morley experiment
No,
that
and
did.
it wasn't as much Einstein as it was everyone else after him.
I know Einstein
Yeah,
tried to save science from
yeah, from not
Bohr.
having an answer,
I mean,
basically.
the worst guy was Bohr,
Yeah, well,
and
Bohr is just total nonsense. He just makes up
yeah,
stuff.
yeah,
He's good at
yeah.
creative writing and maths.
I wouldn't go that far, but yeah, Bohr was the ultimate villain in this story. But everybody, look, the whole world lost their
Yeah,
mind. Be-
not just Bohr, like Bell as well, like Bell's
yeah, but
nonsense.
look,
Absolutely.
once Michelson and Morley got the null result, no one that's it. Everybody lost their mind. And then later, when they were getting all the contradictions in quantum mechanics, it was just a continuation of nothing makes sense because Michelson and Morley failed, and then they started getting crazy results in quantum mechanics. They said, "Oh, okay, the world makes no sense. It's fine. Let's continue with the world that makes no sense."
pays the price.
And Einstein was wrong about so many things that, like, he was right about many things. He was wrong about many things. It's fine. I mean,
Yeah, I don't blame him as much as all the
yeah,
cult like
yeah,
followers.
yeah. Let's see. I really think that Einstein is a practical joker pulling
No, I
the
don't.
legs of
That's
his.
that's that's not it.
No,
That's
let me see. Pulling the legs of his enthusiastic followers more Einsteinish than he.
okay. The second part is true, but the first part is
Oliver Heaviside?
yeah.
Heaviside Heaviside was the guy who actually wrote Maxwell's
Yeah,
equations.
they should be called Maxwell's Heaviside equation.
Yeah.
But yeah, I mean the second part is true. The first part no.
No, no.
No,
It's
the second part is true. Like the followers of Einstein are more believe more in Einstein than he believed in himself.
pulling the
That's
legs of it. Okay, I don't know.
that's no. The second part is true. This is the first part. No, not really.
All
Okay.
and everything we do in physics relies on physical processes of measurement. But despite this, what measurement is and actually means still remains one of the most philosophically underdeveloped branches of science.
I guess that's true. Let me just
It's
see
it's not
how many.
underdeveloped. Like Newton's already solved the problem. Just people don't listen to him.
Uh,
It's
um.
pretty much settled.
Okay.
I'd say.
Even today, people take for granted that they understand what a measurement is telling them, often overlooking or failing altogether to recognize all sorts of hidden implicit assumptions that any process of measurement carries with it. For instance, say you want to make a very basic type of measurement, a measurement of velocity. This measurement would seem to require only four simple
So this is supposed to be a photon. So
Mhm.
instead of showing a photon as a wave, they're going back to a photon as a particle.
But is that supposed to
pieces
be
of
a photon?
You'll see that they're still showing photons as particles.
information, two measurements of spatial displacement, and two readings of temporal durations. Easy, right? Well, no.
I'm
Because
going
to
to leave a video about the Casimir effect for you to watch.
The Casimir effect?
Yes, some
We've
experiments with the Casimir effect and how to measure it and all of that. You'll find it
okay,
interesting, but it's like 2 hours.
okay.
acquire this information in the first place, you also need several additional equally important things. 1. A clear and precise understanding of what is meant by the concepts of spatial position and temporal duration in the first place. And 2. What could be termed an engineering solution for the coordination of those spatio-temporal concepts to the functionings of actual physical objects. Such solutions should be readily familiar to most individuals.
So he's separating the actual notion of a spatial displacement and temporal duration from the tools, from the engineering tools of the ruler, the meter stick, and the clock.
For instance, we can engineer a measure of time via the position of the sun in the sky. The higher the sun is in the sky, the closer it is to noon. The closer the sun is to the horizon, the closer it is to morning or night. The spatial displacement of the sun in the sky thus represents the passage of time. Another familiar solution is the marking out of time via the well-regulated cycling of a system of wound-up gears in a clock or watch, where a certain number of gear cycles gives us a second, a minute, an hour, etc.
I think that it's a very slow and long video, but it really shouldn't be, and it's mostly wrong. But let
Yeah,
me
so far, there's nothing wrong.
Yeah, so far everything is okay.
But of course, neither the position of the sun in the sky nor the number of revolutions of gears in a clock are what we mean when we say time itself.
That's good. I don't know if it's good, so that is what we mean by time. Time has a meaning. The meaning of time,
Yes, it's separating the concept from the measurement.
it's fine, but then you have to say the meaning of time is the measurement. The measurement is the meaning. There is no meaning but the measurement. And the measurement is the engineering solution, like a meter stick or clock or the sun.
The reason for this should be fairly apparent. The gears of any clock will eventually stop moving. And the Earth's rotation, which causes the sun's displacement across the sky, features a number of irregularities, ultimately.
So he's saying because the way we measure time sometimes can break, therefore it's not time.
No, I mean the point is separating the you're nitpicking a bit too much. Like what he means here is to separate the action from the concept. It's just that. There's no point in trying to
no, but no. So, I think he's making a mistake.
No, he's separating the action from the concept. Like
I think that's
measuring time, like how we engineer that action, and the concept of time, which is a little bit different.
So. Okay, let's listen to what he says.
Mainly making it unsuitable for very precise timekeeping. Thus, it would be absurd to assert that the stopping of the gears of a clock meant that time itself had stopped, or that, say, the slowing of the rotation of the Earth somehow meant that time itself was slowing down. Holding this fact in mind, let's revisit the cautionary language of Newton's aforementioned paragraph and see if we can make some sense of it. Consider first the opening line. Relative quantities are not the quantities themselves whose names they bear, but sensible measures of them. Here it seems Newton would be distinguishing between two types of time. There's first what he would probably term relative time, the sort of time that could be engineered from, say, distinguishing the position of the sun at different points in the sky. Indeed, an hour of time on Earth is generally marked.
I don't know. I mean, the word relative. I don't know what Newton meant by relative.
Out by the sun traveling a 15-degree arc-length path
about like velocity and so on than time.
The sky. But this 15-degree arc-length path isn't an hour of time itself. That is, it isn't what Newton would distinguish as actual or absolute time. Rather, instead, this would be what Newton terms the measured quantity. So this measured quantity of the passage of the sun through a 15-degree arc length qualifies in Newton's thinking as relative time. And as he further writes, it's meant to be what he calls a sensible measure of actual time. The meaning of sensible lends itself pretty readily here. The displacement of the sun in the sky is a sensible choice as a physical
Yeah, it's an engineering solution.
Stand-in for time, because it's extraordinarily regular, and for the most part, it doesn't change. Now in this context, the meaning of Newton's warning should seem more self-evident. When we say time, we mean the idealistic stand-in of a perfectly regular process, which itself is never subject to alteration by any other physical processes. And since something like the displacement of the sun in the sky is both caused and affected by other ongoing physical processes, it cannot be what we mean when we say the words time itself, and thus should not, according to Newton.
No. Time must be defined by the way we measure it. There is no way of getting away from that. And you have to include your method of measuring the possibility of it breaking. You have to deal with it as part of your definition of time. Just deal with it. You
But it
don't.
can be a lot of measurements in this case. So you
But
can.
he's
But
saying
still the
he's
way we
saying
measure it, but
no. He's saying the way you measure can break down. Therefore, the measurement cannot be the thing itself. And I'm saying that's. I wouldn't say that. There is no thing itself. The thing itself doesn't exist. Time doesn't exist. There's only measurements of time. Time is an abstract notion. Oh, but we don't have access to abstract notions. All we have is relative is the subjective experience. Let's continue.
Newton's writing be interpreted that way. So what does all this have to do with Einstein? Well, Einstein was very influenced by the philosophy of the Austrian physicist Ernst Mach, who essentially believed that if something isn't observable, that if it can't be measured, then, well, it shouldn't be regarded as real.
Good.
no, not
That's
at all. Terrible.
that's basically Newton.
Absolutely terrible. Absolutely terrible at all levels. Like horrible. As
Why?
as horrible as possible. We
Why?
consider things that we can't measure as real all the time.
I can barely understand what you're saying, by
We
the way.
consider things that we cannot measure as real all the time.
Like what?
And then we consider things that we can't really observe as real as well. We can
Like
consider
what?
that for sure. Things that we can't measure. I mean, for the most part of our history as humans, we had no way of measuring feelings, for example.
Why can you
We
not
could
measure
observe
feelings?
we could observe their effects on other people, but we had no way to measure them. For most part of our history, yes, we had no way to measure them.
Why not?
When Mark was alive, there was no way to measure them.
Why
That's
not?
why
What's
not? There
stopping?
was no way.
What do you mean?
Why?
So you know that you prefer chocolate over vanilla
No,
or
I'm talking about like on other people. You know, but it's still not a measurement. That's still not a measurement. That's
why
not
not?
that's
Why
not a
not?
measurement.
You can ask me what I prefer, vanilla or
Okay. I
chocolate.
can ask you what I prefer, but I have no way if you tell to say it to. It's not an
Ex-
objective measurement. Like
exactly.
it's a subjective question.
Exactly, because
An
we
assessment
have.
is not a measurement.
That's exactly the. But I agree. We have no access to actual, to objective. We have no access. All we have is engineering solutions to measuring. So you can ask.
No, but I can infer whether you're telling the truth or not.
Yes,
For sure,
yes.
I can
But
infer that.
at the end of the day, all you have is.
Either way, there are things that are not observable that you can
Give me
definitely
an example.
logic, for example. You can't observe logic. You can only understand it.
Give me an example.
Logic.
Give me an example of logic.
Give you an example of logic. Like, come on, A equals
Yes.
A. That's an example of logic.
That what?
A equals A. That's an example of logic. I mean,
So
what the hell, an example of logic?
A equals A. That's an example of language, right? Those
Yes,
are
an example of language that makes sense, language that is logical. So I mean, we can understand that to be true, but we can't observe it. It's not an observable thing, but we can understand it to be true. An abstract, like he's literally excluding all abstract concepts from having any bearing on reality, which is ridiculous. Like is excluding a lot of relational things as well from having any effect on reality.
Wait, hold on. So you said A.
No, it's terrible.
Wait, hold on. So you said A equals A is an example of logic. So
An
I said,
example of something that can't be measured and it can't be observed, and yet we know it's true.
wait. So that's, so we noticed right. So it's just a scientific observation that we
No,
noticed.
it's just logic. We understand logic intrinsically. It's just part of our being.
Okay, so when you say A equals A, so I've noticed a phenomenon that when I talk to people
Yeah.
and I ask them for an example of logic, usually they say A equals A. I notice this phenomenon.
Well, it's the simplest one.
No, no,
So,
no, but I'm looking at this as a scientific phenomenon. I'm not.
okay, that's different, but like, what it doesn't invalidate what I said.
I'm I'm saying what you think is logic. I'm saying that's just a social phenomenon.
No, it's not. No, that's not it. No, logic is part of natural relationships like causality and so on that exist in the universe.
Okay, okay. So hold on. So when you say
We,
a,
we our brains have adapted to be able to think logically. That's it's an adaptation. It's like vision or something else. It's just abstract.
okay, let's slow down. So look, I'm sure you believe A equals A is a true statement.
It's not a belief. It's a certainty.
Yeah, and you're convinced of its truth.
Yeah, I mean I'd be
Okay,
stupid otherwise.
okay, but the okay, but let's slow down. So let's really analyze. I just want to I want to make a separation between. I don't want to talk about you, about your belief. I want to talk about the phenomenon, right? I could have
There's no
asked you,
phenomena.
look,
It's not a phenomena thing.
yes. So I classify it as a phenomenon. So I
No,
could have
but it's not a correct classification.
let me give you maybe an example. So sometimes when I ask people, give me an example of a logical statement, of a truthful logical statement, they say the sky is blue.
No, that's a factual statement. That's just wrong. That's horrible. Like that's a failure of the education system.
But you would
That's
agree that, but you would agree that that is
I would
nothing but
agree that the sky is blue, but that's not a logical. It's not logic. That's got nothing to do with logic.
it's a truthful statement.
It is a truthful statement, yes.
So it's it has the value truth assigned to it.
Okay, yeah,
And
but
the
it's a
value
factual
truth,
statement. Like what gives it the truth is our experience of the sky in our
okay,
measure.
but what about
It's a
a,
different type of statement. Like there's
hold
nothing to
on,
do with
okay,
my
hold on.
statement.
But what about A equals A? Isn't that also based on your experience?
No,
You want to tell me
absolutely
that
not.
if you had no experience of the English language, you would have said A equals A?
No, that you now you're confunding the language with the logic. The
Hold on.
language is something. The language is one thing. Like the
Hold on.
language is just the is completely subjective and
Hold.
experience based. No, no, no. Let,
Okay.
let me say this. The language is completely subjective and experience based. Of course,
Okay.
right? Like if no one had invented English, English shouldn't exist. It's an artificial thing. so it can never be naturally understood.
Okay.
Logic is naturally understood by humans. Like
Okay. The
that's
question
completely.
is the question is would you have said A equal A?
No,
A
it's language. No, no, no. We're back to the same. You can't confuse. You can't confuse language with logic.
Hold on. Let me complete the question. Would you have said A equals A if you had no experience of this life?
So I had no experience of this life, but okay, that's a pathological question. Like if that's saying if I wasn't a human being,
So that, but
that
that's so. But my claim
doesn't
is,
make
but
sense.
that's
Yeah.
okay. Okay,
But
so
I
this
can make a claim. I can make a claim counter to that. Like any intelligent being would reach that conclusion, even if they use the completely different language. Even if they
hold
use
on,
clicks as language, or even if they use smell as language,
hold
they
on.
would have
Listen,
to be able
listen,
to reach this conclusion.
listen, listen. Imagine you were a brain in a jar, in a vat, and you never had any experience in the universe. You were not hooked up to any input or output. Would you have said A equals A?
I couldn't have said it or done anything. I wouldn't be alive.
Well, you would be, your brain would be
No,
alive.
no, I'd be alive, but I would not have any conscience of anything. That's ridiculous.
But this is exactly my point. My point is that you say A equals A because of your experience. Just like,
No, it's not because now you no, it's being conscious and saying something based on experience. Are no, they're not the same thing. No, I don't say it
okay,
based on my experience. I
okay,
understand logic naturally.
okay. Let's say
Like
you were,
it's a quality of the human brain to be able to do that. Like little children understand logic. You don't need to teach them logic for lots of at least the most part of them, unless they have some kind of problem with that.
but this is
They
exactly, okay, but this is exactly what I'm asking. So a child, it's already too late. He already has experience of this life. So I want to catch the
and it's
child.
not because of experience so much. Like we've evolved to be able to do this.
That's just experience. The
Well,
evolution.
it is in a way it is experience, but I think we're losing track of what we're talking about. We're
No, no,
talking
no,
now.
no,
We're definitely losing track of what we're talking about.
no, no,
What
no,
now?
no.
Because we're losing track of what Max said. What Max said is like if you want to have this conversation, it's going to be like ultimately everything is formed through evolution, and evolution is experience. Okay,
Yes,
fine. Like we're gonna get there. But what Max said was that we cannot. I don't even remember. We cannot ascertain something as existing unless we
exactly,
can measure it or observe
e-
it, which is false.
exactly. No,
No, it
and
is
this
false.
is, and
And what
this,
you're saying, like
but this is
we
exactly, this is
no,
exactly, this
that's
is
false.
exact.
Like I don't need to have observed anything in my life to know that. It's not an observational thing.
Okay,
Like
so
I
so
can,
we
you can tell me a statement that I've never in my entire life, that I've never in my entire life heard, and I can tell you if it makes sense or not. Like that's no, that's like that's the we have to distinguish. We have to distinguish knowledge by experience. We have to distinguish that from also intuitive knowledge. We have to distinguish that from reasoning. Like is what he's doing is terrible. He's trying to mix like some practical reasoning with observation and saying that's all that exists. That's not true. That's absolutely not true. And the part about feelings that I told you, uh, humans always knew and always were able to infer what other humans were feeling, uh, and they had no way to measure it, and they could not observe that directly. So that's intuitive knowledge. So that's another thing that exists in the world. So Mark is trying to exclude a bunch of things that exist in the world, and it's just bad philosophy. It makes no sense. Okay, still there?
Yeah, yeah, but I'm trying to say something. Look, first of all, what Mark is saying, I completely agree with it, and Newton completely agreed with it. So everyone is in
Okay,
agreement.
I don't agree with him, with them. I
Okay,
don't know if
so
Newton agreed with it, but I
no,
certainly don't agree with this. This
so
is not something I agree.
so so Newton, Mach, and I all agree on this notion
Okay,
that
and I've proven you wrong, so we can move on.
no, you didn't.
Yes, I did absolutely.
No, look,
Well,
if you never right, if you, let's imagine your brain is kept alive.
okay,
You were
fine. Let's not do this. Let's just continue the video. Like I've already heard the argument. I know where the argument goes. It doesn't validate what Mark is saying. Like your position, which is not the same as Mark, is not bad because
my
it's like
position is
you're saying that
identical.
everything comes from the physical world and evolution is experience. So fine, we still can recognize things that we haven't observed or measured. That's still
Who
true.
who says that?
Like it's still it doesn't disprove that part, but it's better than Mark for sure. Like at least
I'm lost.
it includes more than.
I completely lost you. So I'll
Okay,
repeat.
fine. Let's just continue the video. There's
Okay.
no point in
Okay.
arguing.
Okay.
Indeed, the Machian argument against Newtonian space and time goes along the lines that, since absolute space and time aren't observables, our laws of physics shouldn't contain references to them.
Wait, what?
Right.
Is that, since absolute
I
space and
put
time
it forward.
Absolute time can be measured by no comparison with no
Hmm?
motion. It has
Who
therefore
said
neither.
that? Wait, who said that? Like I'm
I
lost here.
guess maybe Mach. Let me see.
No, probably
Absolute.
Newton. Well, let's go back a little bit and slow down the video. There's no point in having the video so fast.
Indeed, the Machian argument against Newtonian space and time goes along the lines that, since absolute space and time
Absolute time can be measured by no comparison with no motion. It has therefore neither a practical nor a scientific value. Exactly.
Wait,
Just
can be measured by no comparison with no motion.
yeah.
Hmm?
So,
How could you measure time without motion? It
but
doesn't make any sense.
so let me just preface this. As soon as someone says absolute, my answer is inaccessible. Absolute anything. I don't care what you put here.
There's
We have
therefore but this is just wrong.
no.
Like
This is
this, I'm looking at the statement, not looking at what you're saying. What you're saying is fine. This statement makes no sense. Zero.
why
Absolute
absolute.
time can be measured by no comparison with no motion. This makes no sense. This is not a statement that makes sense. Whatever this is not a statement that can be read or interpreted.
What he's saying is, I think maybe this is old English. You can just say cannot be measured by comparison
Okay, fine.
with motion. Cannot be measured. Absolute time cannot be measured. It is therefore neither practical nor a scientific
Oh yeah,
value.
it's still wrong. What it should say is absolute time doesn't. What it should say is time doesn't exist.
Time, I agree. Time does not exist.
Okay, fine.
All we
Okay,
have is methods of measuring time. This
time is a
is my
measure. Period.
look.
Like, there's nothing
Look.
more to it.
Look. I spent like this past 2 months. This is actually much more than that. The last couple of years, I've improved my understanding of what science is. And my conclusion is after debating people, if you debate people, you will see that that anytime someone says the word absolute, the answer is inaccessible knowledge. Whatever you tell me, if you want to discuss anything in the absolute sense, My response is that knowledge is inaccessible and for
It
always
depends. We can
no.
know we can absolutely know that 1 plus 1 is 2.
No. You
Yeah.
cannot know anything.
No,
Absolute
actually, no. We
knowledge?
can know absolutely that 1 plus 1 is 2. Like definitional things, we can know absolutely.
No, no. One
Yeah.
plus one is two is just a ritual. It's just a
It's a
social,
definitional thing. It's a definitional thing. We can know those things for sure.
which is a language. It's just a
Yeah,
language.
we can know linguistic things for sure.
It's just
Linguistic
a
or
language.
logical things we can know for sure.
It's just a language, and language is just the evolution of dogs barking, of cavemen growling. It's just a growl.
Not really. I don't
Language,
agree with that.
it's
But
just an evolution. When you hear whales singing, and every animal, when crickets
okay,
make
but
their
we're
noise,
different. We can make sense of our language. So
it's
it
it's just
doesn't mean
it's
different.
just it's just emotions. It's just
No,
instincts. Yeah.
no.
I know you want it to be more, but it's
No,
not.
it's not me that it's not me wanting to be more, is that it is more. For humans it is more. Even for
Mm.
dolphins it's more, like they can actually send locations and stuff like that.
But at the end of the day, it's just emotions. When
No,
you
it's not even for dolphins that's not correct. So
everything. Okay. Anyway,
no, like
let's
this
get
is
let's.
this is not an emotion. Like for example, this sentence has nothing to do with emotion.
Yes, yes, it is. Like
No.
when you speak, when you say no, you're a caveman growling.
Yes,
Obviously,
but
you're getting,
the
you're
caveman
getting,
growl.
you're
But
getting
more or
upset.
less. I
You're
mean,
getting, you're getting upset. I'm getting upset.
no,
These
I'm
are
not getting upset.
yes, yes.
Yeah,
These are
and Mac is not getting upset. He is.
yes, yes. These are just
No,
yes. These are just emotions. The most scientific, the most elaborate, the most logical, the most mathematician that you will ever be. At the end of the day, you'll either be happy or sad when you confront any mathematical or scientific or logical truth or false. It will either make you happy or sad or somewhere in between.
I mean, usually makes me bored.
That's also an emotion.
I mean, like one thing doesn't invalidate the other. I can feel emotions and understand things.
But that's all it is. So it's just emotions. Is where you have to put
No,
things
I
in
I
perspective.
I 100% disagree with that. But let's continue.
Okay,
I definitely
Time
disagree.
aren't
okay.
All our
observables.
principles of mechanics
All
experiment.
our I'll read. Let me read. So all our principles of mechanics are experimental knowledge concerning the relative positions and motions of bodies. Exactly. All the
Mm,
principles are just
Wait,
experiment.
wait, wait. All the principles are experimental knowledge, but concerning the relative positions and motions of bodies, no, that's not true. The last part is not true. No, it's not.
Why? Why not?
Like there are lots of things. There are lots of principles of mechanics that don't correspond to relative motion. In fact, it's pretty much impossible to think about force with relative stuff. Like force is not relative. Velocity, yeah, you can relativize velocity all you want, but force, not really. Mass is not. I mean, it's weird.
So how are
Not
you?
important.
What is force?
What is force? That's a good
Yeah.
question. It's a difficult definition,
So
but
I would,
it's just
but
imparting energy on something. Really,
but I would say you cannot have force without motion.
you cannot have force without motion. You can actually have force without motion. Yeah,
But
you
if
can
you think
definitely have
about it,
force without motion. If you press your two hands against each other, then
but that
you
means
can
the
definitely have force
mole,
without motion.
but that means the molecules in your body are in motion. Your muscles are tensing. There's
No, they can come to a
sugars.
standstill and there still be forces.
But if you look at the molecular actions of your muscles, you will see motion.
like if you're gonna do that, like you can say there's always motion.
Exactly.
Okay, fine, but that's not the but you can not have an increase in motion in that case and still have force. You can still do that.
Mm, you
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 can still do
always
that.
you
You can
always
still
in
you
order to have in order to have
you know
force.
if you have tension on something, sometimes if you have some kind of tension, like it could be electromagnetic or something like that, you can actually reduce the motion of
But
things.
even in order to apply the force, you had to press a button, so you had to move.
Okay, but fine. You can't. One thing is moving, the other thing is relative, right? Like
Hmm?
you can't think about force in relative terms because someone kicking your ass and you moving forward is not the same thing as someone else kicking my balls and me moving backwards.
I can barely understand what you're saying.
Someone
What's
kicking your ass and moving you forward is not the same thing as someone kicking my balls and moving me backwards, right? Like you
mm,
understand what I'm saying? Like
look?
it's not.
We were
You
discussing.
can't look at force and energy as relative. So that's not true. So this is not true. Once again, the
Okay,
first
I
one is
agree.
the first one
I
doesn't. The first one is just saying nothing. The second one is not true.
no. Okay, let's continue.
Our laws of physics shouldn't contain references to them.
Let me get rid of this. Newton has again acted contrary to his expressed intention to investigate actual facts.
Uh, who said that Newton's intention was to investigate actual facts? Maybe he said that. Maybe he didn't. I don't know.
I don't see.
Maybe
I don't
let's
see.
assume that Newton said that. Did he act contrary to this?
I
That we
don't
do not.
see. I don't
No
see
one
how.
can confirm.
I
Did he act contrary to this by saying what he said?
I don't see how Mach disagrees with what we read Newton said. They seem to agree. I don't see the disagreement.
Yes, the to some extent is there's nothing really. There's nothing really. Yes, that's like the last paragraph. He says that Newton acted contrary. I don't know. Maybe he did something else. Maybe he's referring to something else. But
I don't
in
know.
this case, Newton is not acting contrary to investigating actual facts. I don't know what is going on about. It just
Hmm.
makes no sense.
Hmm.
This argument of
Yeah, this video from dialect. I'm
No,
not happy.
I don't know. I don't. I mean, Mac in general doesn't make much sense. So I guess don't blame dialect for that.
Okay, so they shouldn't like. I would never bring up Newton or Mach. I would just whatever you want to bring up. Bring it up. Why do you have to bring up what people said? I don't get it.
Yeah, like
course
lots of
long
people like that. So, but I
predates
don't think the people who like that will watch this. So,
Hmm.
Mach and has many a time proved very persuasive to very many people, including even ourselves at one point.
What? What did he say?
yeah,
Long predates Mach
no, it's
and has many. Our laws of physics shouldn't contain references to them. This argument, of course, long predates Mach and has many a time proved very persuasive to very many people, including even ourselves at one point.
Okay. Oh, the
yeah. Someone
bucket.
needs to put the lid on that bucket. It will solve the problem.
Yeah.
However, the argument itself hinges on some very problematic notions of how words like observable or measurement can even be defined in the first place. Indeed, Einstein, compelled by Mach's ideas, sought to make time and space into what he thought would fit the bill of an observable quantity. But by doing such, he actually committed the very error Newton had warned against. That
This video makes no sense.
No, now is going to make it makes sense. This will make
Okay.
perfect sense. Like
Okay.
Einstein did
Okay.
try to make that, but those are concepts,
I don't
regardless.
think I.
So,
Okay. Let's
but
hear
he
it.
assumed absolute. But in general relativity, he assumes absolute space and absolute time.
Okay.
That is, he sought out a physical process, a measured quantity, to serve as a stand-in for time itself. Now, to his credit, Einstein chose this measured quantity to be the displacement of light between two
You see, he's using the ping pong instead of the
Yeah.
wave.
given endpoints.
So even after they made their previous video about the sound clock,
Yeah, he should
they-
just use a wave.
yeah,
A wise decision since, to the best of our knowledge, light is the agent which is responsible for the transmission of causal information.
like every time he uses waves, I was thinking to myself, oh, finally he's going to say there is ether, but he never said ether. They don't believe in ether.
I think he does.
Hence, most every temporal process that occurs in our universe is at some level a light clock.
That's very interesting that everything is a light clock. He almost says our thesis in the paper.
Yeah.
But Einstein made a huge error in doing this, for he failed to account for the fact that light itself, even in a vacuum, is still a physical
And this is not a good wave to show. You should show like a normal wave. That's not a wave. I don't know what that is. That's not a wave. You should actually show like a sound
line.
wave. No, you should show like a sound wave, like an actual like an ocean wave.
thing, and hence that it could be influenced by other physical processes, known or unknown.
That looks like the ether. Maybe they're suggesting there's ether.
Indeed, just like defining time as the passage of the sun through a certain arc-length path in the sky, defining time as the passage of light between certain endpoints in space would be a terrible definition if it turned out some other physical process, known or unknown, could affect the motion of that light during its passage.
Like ether?
Indeed, earlier we mentioned it would be absurd to assert that time had stopped because the gears of your clock stopped moving, or because the Earth stopped rotating. Yet it is without a sense of absurdity that we make such statements all the time in relativity.
Do you want to finish watching this? Because I think this is nonsense.
No, there's no nonsense here. This is fine.
Okay.
Like, why do you think this is nonsense?
It's nonsense. It's nonsense. There's nothing to do with anything. I like he's
No,
trying to
this
blame.
is good. This is good.
He's trying to blame Einstein for something. I don't know for what, and what is the blame? Like, imagine it's a court case. Let's hear the case. So far I'm not hearing anything.
Time stops at the event horizon of a black hole.
No, it doesn't. No, it doesn't. Well, what are you talking about? If you fall into a black hole, you don't notice that you fell through. So time doesn't stop. That's nonsense.
Time
I
stops
mean,
if you are traveling.
supposedly, if, like, the theory currently accepted.
Your audio is worse than normal. I
Sorry.
can barely tell what you're
The
saying.
theory that's currently accepted, I think it does state that.
No, if you fall into a black hole, you cannot know that you're falling into we could be this universe could be falling into a gigantic black hole right now, and we would never know it. Why would we know it? So no, there's no way to know it.
At the speed of light. But if light is a physical thing and affected by other physical processes, then this is, precisely as Newton put it, a clear violation of language. Time itself does not stop. Clocks do.
He keeps I don't know where he's taking this conversation. Honestly, I don't know what he's trying to say.
I mean, it's making a point.
Now, there are many out there who naively argue that this is the essential point of relativity, that we are ultimately stuck with measured quantities in physics, So why bother with ideal
No, that has nothing to do with relativity. That is called science. That's called life. That's called epistemology. Nothing to do with relativity. Relativity is just wave mechanics, so you can forget about relativity. Let it go.
realistic stand-ins? Hence, one might feel Newton was being dramatic in declaring that by adopting such practices, as Einstein did, that we would be defiling philosophy.
Einstein did not adopt any practice. I don't know what this guy is talking about. I honestly, I don't know. This entire video,
But
it's
no, he's talking about an affirmation made by Einstein.
about what?
Yeah, like Einstein, I mean, he's claiming that Einstein defined time as by using the speed of light, essentially.
No,
Yeah,
no.
yeah, he defines speed
Einstein,
of light as constant, and time is based on that.
no. Time and Einstein discusses using a clock. He doesn't. He talks about the clock at the train station. He doesn't.
Well,
He
but it all depends on like it all depends on the speed of light.
no, not time.
Yeah, time does.
No, no.
Yeah, it's all about.
The
Okay,
speed of
so
light. No, no, no. The way they measure the speed of light is, they measure the speed of light with an external clock. They had this apparatus that had the slits and was ticking and we're getting a reflection or something. Mm, So no, no, no. Look, I don't know what he wants from Einstein. Honestly, like I have complaints, but the complaints are not against Einstein. The complaints are against maybe Michelson. Maybe Michelson is guilty, but even
no,
he
let's
could.
let's not find a guilty. Like one, it's not one person that is guilty.
Fine, then everybody's guilty.
Yeah, it's more
We're
like that.
guilty. We're guilty that we're not fixing it. Everybody's guilty. But this video makes no sense.
philosophical truths. Some clocks tick faster or slower than others. So what? Great. We keep track of which clocks are affected and under what circumstances, and then all is good, right? Well, no, because it gets worse. So much worse. Returning to the Earth for a second, let's say we wanted to claim that the sun's passage through the sky is what actually defines time. Just as Einstein claimed in his famous 1905 paper that a light beam's passage in an inertial frame is what actually defines time.
What? No, he did. He didn't say that a
Mm,
light beam
no,
passage.
really, that's just an equation.
Yeah, time interval is at the bottom. The time interval is determined by. I mean, it's not in this paragraph. It's in like
Um,
page 3 or something that he discusses the
let's
train
see what it
station.
says.
And wait, over here? No, this is irrelevant.
No, no, that's not over there.
This
Probably.
is this is just Faraday's.
Just let the video go forward.
Beam's
Let's see
passage
what
in an
it is.
inertial frame is what actually
Anywhere else?
defines
Light? No.
time.
Wait.
But a light
Wait,
beam's
wait, wait.
passage in an inertial
Okay, stop.
Okay, let me read. The laws by which the states of physical systems undergo change are not affected whether these changes, this is postulate one, whether these changes of state be referred to the one or the other of two systems of coordinates in uniform translatory motion. I guess these are the laws of physics or the laws of Maxwell. Two, I guess this is postulate two. Any ray of light moves in the stationary system of coordinates with the determined velocity c, whether the ray be emitted by stationary
No,
or
but
by.
that's indeed a problem. That's indeed a problem because like time, what time? Like is assuming there is some kind of absolute time and also some kind of absolute length for the speed for light.
No,
Yes, it
no,
is. It has to be. I
no.
mean, you could say that the ratio is always kept.
No, no, no.
That
Here,
I don't know.
hence, let me see. Where
You could say
time
the ratio is
where
always
time
kept.
interval is to
Yeah.
be taken in the sense of the definition in number one.
Okay, number one,
Um,
the laws by which the states of physical
no, it's
phenomena can
not
change.
this one.
No?
No, oh, no, no. I think this squiggly thing that's like, and he uses this in his titles. It's
Oh,
like
okay.
there's a sec. It's maybe section. Maybe this is section one. Anyway, let me see. Let there be given a stationary rigid rod and let its length be L as measured by a measuring rod, which is also stationary.
No, I don't think
You
that's gonna be
know,
anything.
the observer moves. Do you want me to bring up the Einstein's paper?
Yeah, we could see what the definition in one is.
Hmm. Would it be in general? Where did I last paste
I have
it?
no idea. Don't you have it in bookmarks or something?
No, I don't have bookmarks. It could be anywhere. Oh, it's. Oh, he references it in the video.
Oh, good.
Yeah, it's here. Yeah, I went over everything that he mentioned here. This
Probably.
for
Yeah.
Formulab. Okay,
Okay, so where is number one?
this
Okay, this
definition of
is
simultaneity. Let us take a system of coordinates in which the equations of Newtonian mechanics hold good in order to render our presentation more precise and to distinguish this system of coordinates verbally from others which will be introduced hereafter. We call it the stationary system. If a material point is at rest relatively to this system of coordinates, its position can be defined relatively thereto by the employment of rigid standards of measurement and the method of Euclidean geometry and can be expressed in Cartesian coordinates. If we wish to describe the motion of a material point, we give the value of its coordinates as functions of the time. Now we must bear carefully in mind that a mathematical description of this kind has no physical meaning unless we're quite clear as to what we understand by quote time unquote. We have to take into account that all judgments in which time plays a part are always judgments of simultaneous events. If, for instance, I say that train arrives here at 7 o'clock, I mean something like this. The pointing of the small hand of my watch to 7 and the arrival of the train are simultaneous events. It might appear possible to overcome all the difficulties attending the definition of time by substituting the position of the small hand of my watch for time. And in fact, such a definition. So he's saying when we say time, we mean an engineering contraption, like a watch. That's what we mean by time. Time, just like Mach said, there is no time. There's only a clock. But if every time I say clock when I want to say time, that's going to be superfluous or something. And in fact, such a definition is satisfactory when we are concerned with defining a time exclusively for the place where the watch is located. But it is no longer satisfactory when we have to connect in time series of events occurring at different places, or what comes to the same thing, to evaluate the times of events occurring in places remote from the watch, whatever. We might, of course, content ourselves with time values determined by an observer's. I can barely understand what he's saying. So
right. Association together. Coordinates.
It doesn't matter.
No way, the coordinates corresponding and coordinating the corresponding positions of the ends with light signals given out. Oh, so it does that. So it does. So now, so it's not wrong. It does define time based on the speed of light. Yes, it does.
What do you
Okay.
mean? Where? What are you talking about?
Right after you gave up on reading.
We might, of course, content ourselves with time values determined by an observer stationed together with the watch at the origin of the coordinates and coordinating the corresponding positions of the hands with the light signals
Yeah, there. So yeah, is
given out
defining
by
time
every
based
event to
on
be
light. Yeah.
timed and reaching him through empty
So
space.
yeah, he's doing that right there. So we've confirmed that he's doing that.
No, this is
You
just
can go back to the
the
book.
light. You're looking at a clock.
Yeah, he is
The
doing
light.
that.
No, you're looking at the train. When you look at the train, you're looking at the light signals coming from the train. This
Yeah,
is
that's the
nothing.
point. That's
This is
exactly the point.
nothing. No, this is nothing to do with the measurement of time. We might, of course, content
Yeah,
ourselves with time values determined by an observer stationed together with the watch at the origin of the coordinates and coordinating the corresponding positions of the hands. So, I mean,
yeah,
simultaneity.
he's
Yeah,
using
but
light
he's looking.
signals to
No, this is
coordinate
not.
time.
No. This is just simultaneity. Just that he's seeing the train arriving, but he has to observe the train. I think that's what he's referring to. I can barely understand what he's trying to say.
Yes, it
And
is, but it still implies that he's defining time based
no,
on. Yes,
no,
he's defining time based on the speed of
no.
light.
Explain. I don't even know what that would mean. I
What
don't
does
even
it
know what
mean?
that means. I don't know what that
I
means.
mean, it
I
means what
mean,
I said. Like,
no, it doesn't mean anything. I
yes,
don't
it
know what that means. Like I could define time by the barking of the sun. I don't know what it means. The sun doesn't bark. I don't know what you're talking
no, it's
about.
defining time based on the speed of light.
How? How do you define time based on the speed of light? How would you do that? That doesn't make any sense.
Yes,
I cannot.
is defining an absolute time.
How do
In
you
that,
measure? How do you
yes, in
measure?
this
How do
referential
you?
is defining time based on
How?
the speed of light.
How? How do you measure time based on the speed of light? How
Okay,
would you
it
do
measures
that?
time with the clock, right? It still
So that's a
measures time
clock.
with the clock.
So that's a clock. We're done.
But
That's it.
what gives sort of like the mm, the his ability to measure the time on on a remote place is using light for that.
He's using light to
So he's
see,
using light to synchronize. No, he's using light to synchronize.
not to
Yes,
synchronize.
he's synchronizing using the speed of
No.
light.
He's seeing. This is the. He's
He's synchronizing using
no.
the
I
speed of
think this
light.
is the light. No. We might, of course, content ourselves with time values determined by an observer station together with the watch at the origin. So he's with the watch at the origin at coordinate 00 and coordinating the corresponding positions of the hands with light signals
Yeah, he's synchronizing
given
using light.
out by every event to be timed. Okay, so every event gives out a light signal.
Yeah,
This is like in the animations when the train, when the mover, when the person moving, right? There's a train and there is an observer. When the train passes by point X, boom, it gives out a light signal, and then when it passes by point Y, boom, it gives out a light signal.
yeah.
This is nothing to do. What? Yes, this is
No,
nothing to
it's just
do.
synchronization.
Okay, but that's not time. I mean,
Yes,
that.
it is.
Okay,
Absolutely, it is. It's basically like the
let's see.
speed
Okay,
of light
let's
is
see.
basically the source of time. Like if the speed of light was zero, there would be no time. If the speed of light
Okay,
was
let's
1
see.
meter per second and something was 2 meters, it would take 2 seconds.
Okay, let's see. Given out by every event to be timed and reaching him through empty space. But this coordination has the disadvantage that it is not independent of the standpoint of the observer with the watch or clock. Okay,
Okay,
look, I don't want to go into relativity right now. I don't like. I mean, not my favorite theory. So
okay, fine, but we can confirm. We have already confirmed that dialect is accurate.
that what?
Dialect is accurate when he's making his criticism.
No,
Yes, Einstein was actually
no.
correct.
Dialect is not saying anything. He hasn't said anything.
He says that Einstein defines time interval based on the speed of light, and that's true.
No, I don't even
Yes.
know what that means.
Okay, just think about it. But it doesn't matter too much.
Okay,
We can continue, or we can change the video.
the velocity of what? Any ray
Of
of
the
light
velocity of
moves.
velocity c.
Okay, this is
Yeah.
c.
So yes,
So
it should have been c, not velocity.
the velocity, the velocity of the speed of the velocity, meaning the speed of light is right. A light path needs to go from A to B over a time interval t1 to t2. Where time interval is to be taken in the sense of the definition in section 1.
Okay, we can look at the conclusion of section one, just to be sure.
The conclusion of section 1, where
Yeah, the
section
final of section one, the end of section one.
the
Okay,
end
so
of section 1 is it is
in
essential
limited experience, we further assume that the
essential
quantity
to have
2AB,
time
I don't
defined
know
by
what the
means of
MB
stationary
are.
clocks,
Okay.
the stationary system.
2AB this is the two-way speed of light, yes, to be an universal constant, the velocity of light in this space. Yeah, it does that. Okay, so it's confirmed.
But what?
Yeah, he's measuring the two-way speed of light right there. And he defines time based on that. So yeah, he absolutely does that. In fact,
So
he's very explicit about it.
I'm not following what you're trying to
Okay,
say.
so that equation that he has there, you see,
Yes.
that is the measurement of the two-way speed of light. So he
Okay.
considers a constant. He considers the distance from A to be known. So time gets defined in function of that.
What do you mean time? Time is
Yeah,
ta.
the time interval. The the width is
This is the time. This is the time interval.
yes.
He says it is essential to have time defined by means of stationary clocks in the stationary system, and the time now defined being appropriate to the stationary system, we call it the time of the stationary system, but it's defined by a clock, not by the speed of light. You calculate the speed of light based on the reading of a clock, but you use a clock. You don't use the speed of light. You calculate the speed of light from the clock.
But you assume it to be constant.
Fine. But you calculate the speed, whatever constant it is, you calculate it based on a clock.
I mean, but if you know the distance, the only variable is time.
I don't know what you're saying. What?
But if you know the distance, the
Yeah.
only variable is time.
I don't know what you said. Your
Okay, but
your
if you know the
audio.
distance, if you unless it's assuming that you don't know the distance. So
No, no, you know the distance and you measure the time and you get the speed of the speed of light. We know the speed of light. It's 3 times 10 to the 8 meter per second. How do we know it?
okay, but he's
Because
defining time, right?
no, I
Yes, he
mean,
is defining time. That section is the definition of the section to
yeah,
define time.
based on a stationary
It is
clock.
essential to have time defined by means of stationary clocks in the stationary system, and the time now defined being appropriate to the stationary system, we call it the time of the stationary system. So that's the time of the stationary system. I don't know.
Okay, but he uses the clock. He doesn't use the speed of light to measure time. That doesn't make any sense.
I mean, he defines it based on it.
What? He is calculating the speed of light based on time interval, which is based on a clock.
Okay, but you have to remember the postulate that the speed of light is constant to in all referentials.
Yeah, but what is
He's
the
not
value?
really measuring the speed of light.
It's okay for it to.
He's
It's
actually
okay.
defining what time is in that referential just so the speed of light is constant.
No,
Yes,
no.
yes.
What are you talking about? I don't know what
Okay,
you're
so
saying.
the postulate of this theory of relativity
Hmm.
is that the speed of light is always constant, right?
Yeah, yeah.
So it's either defining time or distance. In this case, it's defining time based on the speed of light being a constant.
No, no. The time is based on a clock. Time is always based on a clock. There's no other way to measure time but with a clock. There is no
Okay,
other
but the
way.
speed of light is constant.
So
Remember
what?
that.
So what if the speed of light is a constant?
And this section is defining time.
This is about simultaneity or something. Definition of
Oh,
simultaneity. It's
okay.
just a definition. This is. I don't even know. I don't even know why this is important. But fine, whatever. But it's not about the definition of time. Definition of time is with a clock. You define time with a clock.
You measure time.
Yeah, you define
Okay,
time by
fine, but
measurement.
like we're not really discussing much of anything. I mean, just
No,
discussing
but
kind
that's
of
my
to
point.
conclude that theory.
My
But
point is I
okay.
don't understand dialect.
Inertial frame is what actually defines time.
No, no, I don't know what he's talking about. It's nonsense.
I mean,
Time.
yeah, it's the light path. Really,
No,
that's
Says
defining the
it's
velocity of
not
light.
time. The light path is the path. It's distance. Distance over time. Nothing to the distance and the time are orthogonal. They have nothing to do with each other.
Einstein claimed in his famous 1905 paper that a light beam's passage in an inertial frame is what actually defines time.
No. What are you talking about? I don't know what he's talking about.
Well, the only way you could maintain that position is by denying that there is any causal origin for the sun's movement in the first place.
What? This is complete nonsense. This entire video is nothing but nonsense.
That is, you would have to posit that the sun's daily displacement in the sky was an innate brute fact of nature, the result of, say, perhaps an intrinsic sky geometry that, although it could be readily mapped out with precise mathematical relations, could not be determined to be rooted in anything deeper. Because as soon as you tried to do that, you would be admitting that the sun's passage was not truly time itself, but something more vulgar and physically dependent.
I don't know what he's where he's going with
Is
this.
getting to the point where the speed of light should be something that is more vulgar and dependent.
All he's saying is that the measurement is vulgar, that the measurement of time is vulgar. Therefore, and we have no access to time. That all we have is just the sun, which is a vulgar mechanism. There's nothing deep or intrinsic about the sun and about the mechanics of the sun or a clock. These are just vulgar engineering contraptions, and they basically have nothing to do with time. Time is this god, and all we have is this garbage, which is just a contraption. And and yeah, Yeah, time we time is inaccessible. We don't know what time is. We don't care. As Mark said, we don't care what time is. We don't care. All I care for is what I can measure.
Likewise, to define time as the displacement of light through an inertial reference frame, Einstein had to make this phenomenon acausal, meaning
I don't know what he's talking about. I don't know. I honestly I don't know.
he had to posit that the behavior of light in inertial frames was just a brute fact of reality, with
Yeah, it's a cosmic. He defined it as a cosmic law. The constancy of the speed of light is a cosmic law according to Einstein.
no deeper underlying origin.
Yep, it according to Einstein, the universe, like, first there was the law of the constancy of the speed of light, and the universe was created based on this law. This law is deeper than the existence of the universe. That's what Einstein had in mind, which obviously is lunacy, but that's what everyone believes today.
And since his aim was to force Maxwell's equations to have the same form in every inertial frame of reference, he had to do this for every inertial observer, no matter what their speed was relative to each other.
Basically, he had to come up with wave mechanics without wave mechanics, which is impossible. But
Mhm.
talks
Kind of did.
to what?
He kind of did.
Yeah,
He did his
so that's
best.
not. But that's not Einstein's fault. That's Michelson's fault. That's not even Michelson. That's me and you. We're all guilty of Michelson's failure.
The different notions of time and space, constructed by various observers in different frames, could then be connected via very precise mathematical relations, which,
Yeah, which is garbage. It's just wave mechanics without wave mechanics.
along with the frame invariance of light itself, was soon interpreted to be nothing more than the consequences of an intrinsic Lorentzian geometry which supposedly structures our reality.
Yeah, and reality precedes the universe. So the universe is based on this reality. So, what's the name of this diagram?
Hmm?
What was Einstein's teacher with the space time? Who invented space time? What was his name?
Minkowski or something.
Yeah, Minkowski. Yeah.
Now, if you denied that the
So Minkowski precedes the universe.
sun's passage in the sky was caused by anything deeper, that is, if you elevated it to the status of a postulate, even though you could always describe the sun's
Right. So Einstein posited a postulate that the speed of light is a constant, and a postulate is the deepest thing you can imagine. It's the assumption on which the universe is created.
position and behavior with utter mathematical precision.
This video is complete garbage. I mean, do you want to keep watching it?
I mean, if you don't want to keep watching it, I have
I'm
to
not.
take a shower really quick, so it's a it's a good idea.
What do you have to do?
Take a shower.
Okay. Are you coming back?
Yeah, probably tomorrow.
Okay.
Probably
We
we'll
need to get back to writing the papers, and I
finish
need to
something
discuss
here.
the next thing we need to discuss is this experiment that they conducted. Let me Before you go, let me show you, because that's the next thing we need to discuss. Where is that? Let me open this. Yeah, this guy. So let me go. Let me find. What's the name? Yeah, it's like this satellite that went up like in 2011 or 2004 that confirmed frame dragging.
Confirmed frame dragging.
Yeah. So frame dragging is something that I need to contend with. I need to deal with frame dragging because how do you explain frame dragging with ether? I mean, I saw a really good video, right? It's one of these, yeah. Curvature. This is it. I mean, these are some I found all these amazing channels.
16. Albert In 1916, Albert Einstein proposed that spacetime formed a structure that could curve in the presence of massive.
Right, so we laugh at this. Oh, they're so dumb. They believe in the curvature of space-time, which makes no sense and doesn't even explain an apple falling from the tree. Okay.
Bodies such as planets or stars. In 2004, almost 100 years later, this group of spheres was sent 650 kilometers above the Earth's poles inside a probe, with the objective of demonstrating this theory in an orbital lab.
Okay, so it's above the poles. It's not so. This looks like a geosynchronous orbit, so it's not so high. And this is not above the poles. This is Africa. The pole is over here or over there. But and this is in. Wait, it's if it's above the poles, then there's frame dragging over the poles.
Laboratory free of
In
interference.
which direction?
Here.
Group of spheres was sent 650 kilometers above the Earth's poles inside a probe, with the objective of demonstrating this theory in an orbital laboratory free of interference.
650 kilometers is grazing the atmosphere. So and this is really far. This is basically moon distance where they're taking this picture from. So anyway, but it's supposed to be over the poles. Over the poles means that you're flying over the pole and then over the equator, over the pole, over the equator.
Although the probe obtained positive results, its journey was not without setbacks, so prepare your brain cells, because we are about to embark on a story that, although it began as a relatively simple idea, required almost 50 years of development, the joint work of more than 100 scientists, doctoral students and engineers, and cost $750 million.
Can you skip that part, please?
This is the story of gravity probe.
What?
Just go. Like these
and how
introductions are so boring.
it managed to measure the curvature of space-time generated by our own planet's gravity. The theory of relativity is a great physical formulation that seeks to explain the behavior of the different physical factors that make up our reality from 2 points of view.
No,
It's too fast?
no. They explain the theory of relativity.
Oh.
The special theory of relativity and the general theory of relativity. The first one disregards the effects of gravity, being understood as an extension of the Newtonian mechanics that most people know, but proposing 2 new postulates, the principle of relativity and the invariance of the speed of light. On the other hand, the general theory of relativity seeks to explain how gravity interacts with the different physical factors present in reality, describing a relationship between gravity and the geometric deformation of spacetime. Despite the transcendental nature of the general theory of relativity, which has set the precedence in modern physics, it has been Einstein's least tested theory because, as Kip Thorne, Nobel laureate in physics and producer of the movie Interstellar, said, in the realm of black holes and the universe, the language of general relativity is spoken, and it is spoken loudly. But in our tiny solar system, the effects of general relativity are but whispers. In other words, on the scale we are on, the effects of gravity on spacetime are so small that it is extremely difficult to prove that they are even there. On the one hand, if we focus on large-scale demonstrations, in other words, at the galactic level, when 2 galaxies are aligned with respect to an observer, the gravity generated by the nearest galaxy distorts the spacetime around it, acting as a gravitational lens, to the point of allowing us to visualize the galaxy behind it in the form of a ring. In fact, it is precisely because this phenomenon.
So gravitational lensing is very easy for me to explain using the ether. That's fine. Because the ether flows into a galaxy and therefore it curves the light beams, which creates a lens, which makes sense.
Demonstrates the theory of relativity that they are called Einstein's rings. On the other hand, if we focus on the effects of gravity in spacetime at a low scale, such as at the level of our own solar system, during the last 90 years there have been multiple tests to prove this theory with results that suggest that Einstein was on the right track. However, the problem with all these measurements is that the signals were extracted from systems with significant background noise, and therefore their results could not be considered conclusive. In order to get rid of any kind of interference in the measurements and to obtain once and for all the confirmation that gravity was capable of curving spacetime even at the smallest scales, in 1959 the Gravity Probe space mission was proposed. Its objective was to verify 2 effects derived from the theory of general relativity: the geodesic effect and frame dragging.
This is very interesting. So it was aimed to prove 2 things: geodesic effect and frame dragging.
First, the geodesic effect predicts that a massive body and its corresponding gravity will generate a curvature in spacetime. One way to visualize this phenomenon is to imagine spacetime as an elastic material, which in the absence of gravity remains perfectly flat. but when affected by the gravity of a massive body such as our own planet or a star, it is curved. And this curvature of space-time is responsible for objects such as the moon orbiting around the planet Earth, and these in turn orbit around the sun. On the other hand, frame dragging, which was postulated by the Austrian physicists Joseph Lenz and Hans Thirring 2 years after the publication of the general theory of relativity, states that, in addition to the deformation of space-time generated by the massive body itself, this body is also dragged when the object is rotating.
So this is why they need to be over the poles, because at the poles you would notice the frame dragging. Because only when you look
States that, in addition to the deformation of space-time generated by the massive body itself, this
only when you look from the perspective of the pole do you see the frame dragging. Do you understand?
Right. Oh, okay. I mean, it's the best place to see it.
Yeah.
this body is also dragged when the object is rotating. Understanding this, we can finally talk about the details of the mission and how
Wait,
But how would you-
Why does it have to be on the pole? Why can't it be on the equator or something like that?
I don't know, but how would I
Just go back
explain
a little bit.
but how would I explain frame dragging using the ether? Because they got
Let's go back. Let me see first.
affected by the gravity of a massive body such as our own planet or a star, it is curved. And this curvature of space-time is responsible for objects such as the moon orbiting around the planet Earth, and these in turn orbit around the sun. On the other hand, frame dragging, which was postulated by the Austrian physicists Joseph Lenz and Hans Thirring 2 years after the publication of the general theory of relativity, states that, in addition to the deformation of space-time generated by the massive body itself, this body is also dragged when the object is rotating. Understanding this, we can finally talk about the details postulated by the Austrian physicists Joseph Lenz and Hans Thirring 2 years after the publication of the general theory of relativity, states that, in addition to the deformation of space-time generated by the massive body itself, this body
So in addition to the deformation, not only is it deformed,
is also dragged when the object is rotating.
but it's also dragged when the object is rotating. Why? Why would that happen?
They imagined it.
No, but they got positive results. They predicted and they got exactly what they predicted within very small errors.
Understanding this, we can finally talk about the details of the mission and how exactly it was expected to demonstrate that such effects existed in reality. The principle of the experiment is based on the conservation of angular momentum, which as we saw in the video on gyroscopes, tells us that an object in rotation has an angular momentum represented by a vector in the direction of its axis of rotation, and that in turn this angular momentum will remain constant if there are no forces that generate a torque on the rotating object. It is a phenomenon that we can see in common objects such as a spinning top, which is able to maintain a vertical position while rotating, but becomes unstable once it loses speed and its angular momentum decreases. So, in theory, if we were to spin an object like this sphere, eliminate any torque or interference that might affect its angular momentum, and then orbit it around the planet Earth, we could measure the curvature of spacetime. How, exactly? If we were to orbit this disk around the Earth and ignore everything we have discussed so far about the theory of relativity, what would happen is that the angular momentum should always point in exactly the same direction. However, if the theory of relativity is applicable to our scale, and the gravity of our planet is capable of bending spacetime, then, from our perspective, the angular momentum would be modified, because from the perspective of the sphere, it would have traveled a shorter distance.
So he didn't draw the diagram correctly because he's supposed to fly over the pole and there's supposed to be frame dragging, and the frame dragging is supposed to reorient the direction. So everything in this diagram, I think, is incorrect. He's supposed to show the frame dragging, but he's supposed to go over from left to right and right to left. He's supposed to go over the pole and experience the frame dragging. If he's over here, I don't think he's going to, I don't know. And then when he's here at the very pole, I think there is maybe maximum frame dragging. I don't know, or something. I don't know.
I know, surely at this moment your brain cells are exploding. Using an example that Kip Thorne himself presented in a conference related to the gravity probe, one way to visualize the expected results of this experiment is to plot the direction of the gyroscope on a plane, which represents spacetime without being curved and therefore will always point in the same direction. In this way, when considering that our planet curves the spacetime around it, this same paper becomes something similar to a cone, which means we should cut a small part of it and join its ends, with which the distance traveled by the gyroscope becomes slightly smaller than if there were.
I have no idea what he's talking about, nor can I imagine how this can happen with the ether.
Why not? Just dragging.
But the ether flows in at 11 kilometers a second
With the
everywhere.
rotation of the Earth, there would be a slight. There would be like a.
Why would there be? How? Why would there be anything?
Just relative motion.
What do you mean?
between the ether and the earth. Yeah.
Why would the
The earth
ether?
rotates.
Why would the ether experience frame dragging by the Earth? The ether
No,
flows
the
in.
ether is the frame dragging
Why? Why is the ether frame dragged by the Earth? Why is the ether?
because the
Why-
earth is rotating.
So what?
I don't know. If the earth attracts the ether, it could curve it a little bit, I guess.
No. I don't believe in curvature. I believe in the motion of the ether. For me, the ether flows in at 11 kilometers a second. Why would it experience frame dragging? So you could say maybe a very, very tiny bit. And I guess that's what they're measuring or something. Look, my theory agrees with theirs. I'm not denying general relativity. All I'm saying is when they say curvature, I say flow. I say flux. That's the difference. But I'm trying to understand I'm trying to understand their prediction. So we need to understand. I have to understand their prediction.
or no gravity, generating internal lag in the direction of the gyroscope. An important detail of the mission, as I mentioned previously, is that it was intended to measure the geodesic effect and frame dragging, each of which would curve space-time in a different way, making it difficult to differentiate which part of the gyroscope deflection would correspond to each of them. Fortunately, the solution was quite simple and clever. The way to separate the effects was to make the gyroscopes follow a polar orbit, that is, a trajectory perpendicular to the Earth's rotation axis.
Perpendicular to the Earth rotation axis. Finally, he's showing it correctly.
Thus, when analyzing the displacement of the gyroscope direction with respect to the original direction, the deformation generated by frame dragging would relate only to the displacement orthogonal to the orbital plane of the satellite, while the deformation generated by the geodesic effect would relate only to the displacement parallel to the orbital plane of the satellite. In this last part,
So the blue is the geodesic effect, and the red is the frame dragging. So the frame dragging would only occur when it's at the equator, basically. And the geodesic would only occur when it's at the North Pole. So this thing is rotating. This gyroscope is rotating and it's pointing. In the beginning, it was pointing, let's say, straight at us. Over time, because of the red frame dragging, it starts pointing at the same direction that the Earth is rotating. And also, it starts pointing up. Why is it pointing up? Do you have to go?
No, just continue.
No,
But like, why is it? I was a bit lost now. Yeah.
so they start with a gyroscope. This ball, he's going to explain exactly how they made it. So it's rotating. So it's a gyroscope. Over the satellite goes up over the pole and then back down from the other side. So this is now when it's at the equator, I think. At the equator, it should change its direction. It says here original direction. This doesn't make any sense. This is the final direction. Originally, let's say it was pointing at us. Over time, it would start pointing with the direction of the rotation of the Earth. It's going to point more and more and more and more horizontal. Like if it starts, well, if it starts at it, when it's over this spot, it's pointing at us. Over time, every time we look at it, it's going to tip more and more to the right until finally it's going to become completely.
Okay, but this could be something else.
No. Over time, it will become completely horizontal, or it's
Okay.
going to point It's over time. It's going to point exactly at the direction of the frame dragging with asymptotically. It's going to asymptotically approach the direction of the frame dragging, of the angle that we saw before. Like over time, where is that? Maybe it's over
Yeah,
here.
but why can that not be explained by gravity acting
No,
on the thing?
no. I mean, it's a gyroscope. Nothing can influence the gyroscope.
Why not?
I'm saying, I mean, so except for the frame dragging, except for the curvature of space itself.
Not necessarily. Like the gyroscope wants to fall to the earth.
No, a gyroscope always points at the same direction. Okay, I'm gonna let him explain. But the point is, the red part I understand. The red part, the frame dragging, I completely understand. I still don't know how I'll be able to explain it using ether, but that's fine. The purple, the geodesic, this is reversed. This should be geodesic effect. The geodesic effect. Why is it pointing up? So
It's this is like rotation pointing. Rotation pointing up means it's perpendicular to that arrow.
no, but what is okay? So this is rotating with the right hand rule. It's rotating counterclockwise. So in the
Okay.
beginning, it was pointing directly at us every time it passed over this point on the planet. Over time, wait, but this doesn't make any sense. Why would this change? This doesn't make any sense because every time it goes up and then on the other side, the frame dragging is in the other direction. Oh, it would have the same effect because over here it points to the right. On the other side, it also points to the right.
Yeah.
Because over here it's spinning this way, over there it's spinning the other way, but the frame angle is still this. It's always the same angle. So the red, I can understand the red. Now this is the direction of motion. So this thing is spinning and it's moving this way upward over the pole. Okay, so that's why it's pointing up. But then on the other side, it's going to be moving down and then up again. So I don't understand the geodesic effect. Geodesic just means the trajectory. Geodesic is just the line of the orbit. A geodesic is a straight line. So a satellite is always moving in a straight line. The fact that it curves around the Earth, it's still it's a quote straight unquote line. It's the principle of least action. Like it chooses an orbit. An orbit is, according to the principle of least action, is a straight line. If you define straight by the path of least action. The definition of a straight line is the path of least action. If that's a definition, then an orbit is a straight line, which is that's the definition of a geodesic. But why is it pointing up? I mean, when it's flying this way towards the North Pole, why is it pointing up? I don't get it. Because on the other side, it's going to be moving down and then up again and then down again. I don't understand this pointing. Anyway, maybe he'll explain it.
Pointing up is rotating Is it? Wait. I think it's rotating in the perpendicular direction. I think that's what they mean. Or maybe not.
I don't know. Let's listen. He's gonna explain everything.
The original direction of the gyroscope to be used as a reference is of great relevance, because without it we cannot measure the displacement. However, maintaining a reference point in an experiment that is trying to demonstrate the distortion of spacetime is not something common. To solve this, a telescope was integrated to point at a distant star, and Pegasi, using it as a guide to maintain a stable orientation of the probe during the entire mission. That is, approximately 16 months, a period during which it would make more than 6,000 orbits around the Earth. At this point, knowing what you want to measure and how to measure it is only half the job, since all the theoretical calculations and planning are of little use if the instruments are not accurate enough.
Okay, so it was always pointing at I am Pegasi. In Pegasi. So it was always it started pointing at Impegasi, and then over 16 months it changed its direction. How did that happen? That is weird, and they predicted it.
Approximately 16 months, a period during which it would make more than 6,000 orbits around the Earth. At this point, knowing what you want to measure and how to measure it is only half the job, since all the theoretical calculations and planning are of little use if the instruments are not accurate enough. All these experiments mentioned above were under the assumption that the gyroscope to be used would not be affected by any kind of torque or interference that could change its angular momentum, ensuring that any change in its direction corresponds only to the effects of gravity. Obviously, this would only be possible in theory, but that didn't stop the developers of this project from doing their best to get closer to that goal. At the beginning of the video, I mentioned that the gravity probe's gyroscope was the most accurate man-made gyroscope at the time of the mission, but how accurate exactly? The accuracy of a gyroscope actually refers to the stability of its angular momentum and is measured by a rate of deflection, meaning how many degrees of angular variation you have in a certain period of time. To give you an idea of the level of perfection of the gravity probe B gyroscopes, their rate of deflection was more than 10 orders.
What is this? ESG on Earth, unmodeled drift. Oh, these are drift rates, degrees per hour. GPB gyro. What is modeled and unmodeled? Frame dragging precession. Degrees per hour. So this is 1 degree per hour. What is ESG on Earth? Best laser gyro. What's a laser gyro? Geodetic precession. GBP gyro. Anyway, the name of this, how this demonstrated the curvature of space-time. Oh, this is called Gravity Probe B. That's the name of this mission.
Orders of magnitude less than that of the best laser gyroscope available at the time.
Okay, so this is, oh, there it is. Gravity Probe B. Okay, GPB is Gravity Probe B. Gyro is 10 to the negative 12 degrees per hour. Okay.
This means a rate of deflection 10 million times less. It may seem exaggerated, but it was absolutely necessary to reach those levels of perfection to even be able to detect geodesic and frame dragging effects. The way this absurdly high level of accuracy was achieved was by using these ping-pong ball-sized quartz spheres, with a little help from other systems, but let's take it one step at a time. If we focus on the spheres, the decision to use quartz was mainly due to the fact that it is an extremely stable material over time, both chemically and structurally, thus eliminating possible variations due to its degradation during the development of the experiment. The quartz was then melted, machined, and polished to have the shape of a perfect and homogeneous sphere, having its center of mass exactly at the same point as its geometric center, eliminating possible vibrations that could affect the measurements or other systems used during the experiment, because as history has taught us, a system rotating at high speeds with an imbalance in its center of mass can have catastrophic results. This quartz sphere was coated with a thin layer of niobium, a material that at low temperatures becomes a superconductor, being vital for the operation of the system due to two reasons that I will explain in a few moments. Each of these spheres was covered by two pieces of quartz made with similar levels of precision, achieving that the space between these pieces was only 31 micrometers. This housing, in turn, integrated
31 micrometers. I think you can feel it with your touch.
precision, achieving that the space between these pieces was only 31 micrometers. This housing, in turn, integrated three systems. The first of these was the electrostatic suspension system, whose objective was to avoid any type of contact between the sphere and the housing, making it levitate in the center, thus eliminating possible friction that could affect the angular momentum. This system consisted of three pairs of electrodes located around the sphere, each of which was responsible for measuring and controlling the position of the sphere inside the housing cavity on a certain axis. This process was carried out at a frequency of 37,000 times per second and was possible because the niobium provided a layer of conductive material that could be affected by these electrodes. The second system integrated in this compartment was in charge of rotating the sphere up to a frequency of 80 revolutions per second at the beginning of the experiment to generate the angular momentum of which we have spoken so much. This was composed of two ducts, one through which pressurized gas entered the small space available between the spheres and the housing, making them rotate, and another through which the gas was extracted. Once the desired velocity.
So like one of these dots is the input and the other one is the output. So they input gas and they extracted the gas just to rotate it initially to whatever speed. and then they sealed, and then they removed the gas and sealed it. Are you following?
Mhm. I was almost fell asleep.
Oh, do you want to go? Do you want to go?
No, you just say it again. It's fine.
I mean, this is just very interesting technology. Like, how did they spin up this ball?
Oh, okay,
So
well, that's fine. I don't need to know that.
yeah, yeah.
Had been reached, this same duct was used to extract the remaining gas particles, generating a vacuum in the housing, eliminating another factor that could affect the initial angular momentum of the spheres. The third system integrated in the housing is the angular momentum measurement system, which works thanks to a property of superconductors, in which a rotating sphere of this material spontaneously generates a magnetic field that is perfectly aligned with its axis of rotation and whose intensity is directly related to the rotational speed. Thus, by measuring this magnetic field, it was possible to calculate the angular momentum of the sphere. For this purpose, the housing cavity integrated a circuit of conductive material that surrounded the spheres and that was connected to a superconducting quantum interference device, or simply SQUID, which fulfilled precisely that function while applying diverse measures to reduce interferences in the results. These gyroscopes were also immersed in a gigantic tank of liquid helium to isolate the systems from external influences and keep the niobium at temperatures low enough to maintain its superconducting state. And as if all the measurements mentioned so far were not enough, the gravity probe B included 4 gyroscopes exactly the same, this in order to have a redundancy in the measurements and thus be able to detect anomalies that could occur, a very wise decision, because that is exactly what happened. The gyroscopes were affected by multiple unforeseen events, the most notable being...
Are you sleeping?
No.
Anyway, he shows 4, but 2 of them are horizontal and 2 are vertical. Like,
Okay.
why didn't they do 3? Like 1 horizontal, 1 vertical, like in each of the 3 axes? I don't understand, but fine.
Very wise decision, because that is exactly what happened. The gyroscopes were affected by multiple unforeseen events, the most notable being one that caused the spheres to occasionally have random changes in their orientation, forcing the scientists in charge of the project to extend the mission to take extra data on what was causing these problems, in addition to requiring years of analysis to ensure that the calculations made considered all the variables of the experiment. Having launched the gravity probe B in 2004, the final results were only presented in 2011. Of the 4 integrated gyroscopes, the second one was the most affected by the previously mentioned phenomena, causing greater uncertainty in the results and reducing the reliability of the experiment, especially for the analysis of the deformation generated by the frame dragging, whose expected variation was much smaller than that of the geodetic effect. Anyway, how do the results compare with what is predicted by the theory of relativity? As we can see in this table, the experimental results are quite close to the theoretical predictions.
Quite close. So this is the prediction: 6606.1 negative. What is
Yeah,
RWE?
no. Okay.
What is
It's
you want to
pretty
go?
close. No, it's pretty close.
What is RNS? What is NS? And what is WE? Oh, north, south, west, east.
Yeah.
What is mass per year? What is mass?
That's pretty okay. I don't know. Mass per second. That's interesting. Mass per time.
Like, what are we measuring in this experiment? What is R? R north south. So we saw that 2 of them are. No, he says 1, 2. He doesn't distinguish between the 2 pairs. Joint. See text. What is joint? Anyway, so GR prediction is 6606.1. And you see everything is basically, I mean, this is 6601, 65, 66, 67, 66. Everything is around 66 except for 2, which is 67. Now over here it's expected 39, 37, 49,
There
25.
it's a little bit.
What?
I mean, there the effects are small, but
But look, he's predicting 39. The joint is 37. I think the joint is the average. So the average is very close.
no, but
to
there's a lot of
expected.
discrepancy. But it's probably just the error.
Yeah, but you take the
I mean,
average.
if the error can range from 50 to 15, that's it's not
No,
great.
no, because they said number 2 broke basically.
Okay, then it's a little bit better.
Yeah. Look, I don't know. I don't know what these units are, so I don't know like What are we measuring? Like I would assume degrees per year or
No,
something.
that's F. It's no, that's R. R is radians or something.
Oh, radians.
Yeah, radians.
But it's too many. It's too many radians.
Yeah, that's too many radians. I don't know. No, but it says MAS per year.
Oh, it cannot be radians because this is the
Yeah,
unit.
MAS.
This is the direction. This is the ball itself, the unit, the north-south unit, the vertical unit, and the horizontal unit. R
What
just
is
means
MAS? Just ask ChatGPT or something.
MAS per year.
Yeah.
Oh, milli-arc seconds per year. Milli-arc seconds. Okay. So, what is an arc? Milli-arc second mass. A milli-arc second is a very small angular measurement. It is 1/1000th of an arc second, where one arc second, denoted by two apostrophes, is 1/3600 of a degree. Okay, so it's 1/3600 of a degree. That's an arc second. Therefore, 1 milliarc, so an arc second is 1/3600. A milliarc second is 1/1000 of 1/3600 of a degree per year. Okay. So it's really, really tiny, but it's an angle. It's okay, milliarc second per year. Okay, it's really, really, really tiny. It's barely noticeable. It's fine. Where is it? Okay. Interesting. What is plus or minus? The error? This doesn't make any
Yeah.
sense. How is this the error?
Yeah, that's the error. The errors are very high.
I mean, the error here is bigger than the value.
Yeah.
Okay, let's
But
continue.
the second one doesn't matter.
What?
The second one doesn't matter.
Okay.
That the effects of gravity in space-time can also be detected at relatively small scales such as the vicinity of our own planet, and thus improving the understanding of the rules that govern our reality. While this story seems to end with a happy ending, the truth is that it also has a sad side. Since this experiment was first proposed in 1959 and the development lasted more than 40 years, in that time other experiments were proposed with the same objective, taking advantage of the new technologies available and analyzing the problem with new eyes. More specifically, the Laser Geodynamic Satellite Project, LAGEOS, launched 2 missions, one in 1976 and one in 1992, with the objective of performing multiple experiments on the orbit of the planet Earth, including one in 2004 that aimed to measure frame dragging. The project successfully performed the experiments, achieving much higher accuracies than those of Gravity Probe B. In fact, these satellites are still active performing various experiments to this day. So, all the work done and the millions of dollars invested were pointless? Well, I wouldn't say that. Analyzing the same phenomenon using two different methods can be equally or even more valuable than demonstrating a single phenomenon with high precision. Moreover, when a mission is developed on this scale, the benefits are not limited to the results of the experiment. All the technologies developed to meet the requirements, as well as the theoretical models and data analysis tools, become available for use in future missions, accelerating their development or even opening the door to the analysis of other previously unthought of challenges. For example, the definition of the kilogram as a unit of measurement is currently based on the realization of a perfect.
So he's saying, so what did we get out of it? Because they already performed this experiment apparently multiple times before that. So he says, well, look at this. We redefined what a kilogram is. That's like that. So don't feel bad that billions of dollars were wasted.
Sphere of silicon whose precision is such that it is possible to estimate the number of atoms that compose it. In this way, by having an object of known dimensions and atomic composition, the unit of weight can be defined, eliminating other factors such as the possible variation of its composition over time, a problem that existed in the old definition of the kilogram. In this way, two problems from totally different areas could be solved using similar technologies, so even if your plans do not turn out as expected, remember that what you learn along the way also has value. I got philosophical already, so let's leave the video until here. This was a very different video from what
Anyway, so this channel is unbelievable. There's many channels like it. They have these amazing videos where they explain these super duper complicated things with beautiful animations. So, what is an X-ray?
X-rays are used in a wide variety of device elements, but we will say I want to thank range of used
Amazing.
metal way you can win website exactly Aaron the give. Secondly, they have the ability to
Of course, he shows photons as particles.
ionize some of due to these, but at the same time or genetic device main way to achievement is it's deflected that it's magnetosed of the
It's
velocity
actually
before and after the collision.
not a simple explanation of an X-ray. Anyway, you want to go to sleep?
Yeah.
Wait, you just fell asleep? You just
Yeah, I just
snored?
fell asleep.
That's funny. All right, man. Thank you
All
for
right, see you.
hanging out. I'll see you tomorrow.
See ya.
All right, bye. All right. Okay. Oh, we have comments in the comment section. So Gary says, what? Louis says, the world is flat. A Jobs SBSS. I don't know. Anyway, there's 3 people watching. I hope everyone enjoyed themselves. So let me just add the comment what we just reviewed, that we went over frame dragging. Where's the frame dragging? This guy. So we reviewed that, and we just reviewed frame dragging, responding to dialects, Einstein, this and that. Also this. And where is the link? Is here. Okay. All right, everyone. Thank you very much for watching, and we'll see you tomorrow. Or maybe I'll come back later.